Welcome to Topic 6.6 in Statistical Design and Planning, Statistical Inference in Planning. By the end of this topic, we hope that you'll be able to define statistical inference, describe sampling schemes, and understand the relationship between sample size, error, and power, perform the steps in hypothesis testing and creating confidence intervals, define types of error and power, including sensitivity and specificity, and use OpenEpi for sample size and power calculations and hypothesis testing. When we are conducting research, we want to understand a population, but investigators can rarely evaluate every member of an entire population, so we take a sample of that population and make conclusions about the population from the measures in our sample. This is statistical inference. Statistical inference is defined as the process of drawing some conclusion about a population using the information contained in a sample of that population. First, we sample the population of interest. We then make observations of the characteristics of the sample, calculate measures of their distribution, and estimate the population parameters. Then use 95% confidence intervals and hypothesis testing to make a statement about how confident we are that our estimates reflect the population estimates, taking into account error and imprecision. And finally, we make inferences about the population from these data. We can then use our data to say something or make an inference with confidence from our hypothesis testing and confidence intervals about a whole, which is the population, based on the study of only a few, the sample. The first step is to sample the population. So how do we sample, and what makes a sample good? A sample is good if it represents the population. We use sample statistics like means, standard deviations, medians, and interquartile ranges to estimate parameters for the entire population. There are two types of sampling techniques. In probability sampling, the probability of selecting each member of the population is known. This is highly desirable because it allows for the most generalizability from your sample to the population, but it can be challenging to implement when you don't have a well-defined population or access to every member. In non-probability sampling, the probability of selecting each member of the population is not known. It's less complicated and can be less expensive, but it's also limited in generalizability and that your sample may not be the best representation of your population. But it can be a good method for reaching specific specialized populations. Probability sampling designs include simple random sampling, systematic sampling, stratified random sampling, and cluster sampling. In simple random sampling, every member of a population has an equal chance of being selected. Pulling names out of a hat is the most recognizable example of this technique. For study sampling, this can be done by using random number tables or generators, which are easy to find online, or with statistical software packages. One example might be that you want to sample a population of a school with 300 children, and you want to select 10% of them for a sample of 30. You can put all of the children's names in a hat, or randomize them in a software program, and pick 30 until you have your sample. When a list of the members of a population is readily available, you can use systematic sampling by having the researcher choose every kth member of the list for the sample. In this strategy, the first member of the sample must be determined randomly. If we return to our school example, you take a numbered list of all the children in the school. You choose a number randomly and begin by selecting the child at that number in the list, then every 10th child on the list for your sample to get 30. In stratified random sampling, you divide your population into strata and then draw subjects randomly from each stratum. This strategy is good for making sure your sample is diverse by dividing into groups based on that diversity and sampling each, or for stratifying by levels of an effect modifier like socioeconomic status or levels of a specific behavior. You may also do this if you need to use different data collection methods for different groups. For instance, dividing a sample into children with access to the internet and those without to administer an online versus a paper survey. In our school population, perhaps we know that there's a lot of wealth inequality in the children who attend the school, so you divide them into 3 strata of family wealth and then take a random sample from each strata. Cluster sampling is often used when your sample can be made up of naturally occurring groups like schools or communities. You have a population of the clusters, select clusters within that cluster randomly, and then sample everyone in that cluster group. For our example, you may select one primary school from each region of Lao PDR and then include all children in that school. Finally, our non-probability sampling techniques include convenience sampling, which is using whichever subjects are available, like going to a shopping center and asking people if they'll participate. In snowball sampling, participants in a study refer others into the study. This is a great strategy for reaching some populations that might be harder to reach or in which you need to build trust or work with trust in the population to build a sample. This technique is used often when researching populations involved in illegal or stigmatized activities like drug use or sex work, but can also be used to build samples in rural areas or places where it's difficult to reach each individual. Now we know how to sample, but how do we sample in a way that reduces the impact of error on our conclusions? Study results will vary depending on who is actually in the study sample. This is called sampling variability. There's always a possibility that the estimate will differ from the true magnitude simply because of chance, or this sample variability. And we have to take this chance into account when we describe our data. The sample mean and variance are an estimate of the population mean and variance. X bar is called an estimator of the parameter mu. If mu is the mean in the population, the true mean, X bar is the mean in our sample. We want to use our sample size and mean and standard deviation to estimate the value of a population parameter and determine whether it's equal to some specific value. That is the goal of our second step in making observations of variables and estimating the population parameters. So how do we quantify this uncertainty or degree of imprecision in the estimate when we don't know the true values? It depends on 2 variables. Variance or standard deviation. So if we have a homogeneous random sample where everyone is kind of similar with only a small amount of variability about the mean, that sample mean will be closer to the actual true population mean. It also depends on sample size. If we have a large sample size, regardless of the variation, the difference of the individual values in the sample will cancel themselves out and the estimate will also be closer to the population mean. Sample size is related to the expected distribution of variables in the population. The central limit theorem tells us that in samples that are at least 25, the distribution of a variable in the sample will be approximately normal regardless of the underlying distribution. In addition, it says that the mean of the sampling distribution is identical to the population mean, and the standard deviation of the sample means is equal to the standard deviation of the population mean divided by the square root of the sample size. What this means for us is that, 1, we can expect our sample means to reflect the population mean, and 2, that if we make sure that we take samples of n equals or is greater than 25, we can assume that the sample means will have a normal distribution, no matter what the distribution actually looks like in the population. Now we know a sample should be representative of its population and how we can sample the population. We know that a sample statistic is used to estimate the corresponding population parameter, and that the larger the sample size, the more precise or less variable is the statistic. We focused on point estimates or a single statistic like means and proportions, or in other topics on measuring risk ratios and odds ratios. Now we want to know how well that estimate represents the population. What confidence do we have that our estimates represent the population parameters and are not due to chance or error? We can better answer this by using 95% confidence intervals and hypothesis testing to make a statement about the population from our sample. We use hypothesis testing to determine whether the value of the population parameter is equal to some specific value. When we wish to test whether the data provides significant evidence against some statement about the population from which the data were sampled, which is the null hypothesis, which we often refer to as H0. And we're concerned here with statistical significance, not scientific or medical or economic or philosophical significance. A statistically significant result means that the sample statistic that we've observed is very unlikely to have occurred if the null hypothesis were true. Assuming that our model of the data is correct, that is, that our statistical assumptions are true. There's a difference between a theoretical hypothesis and a statistical hypothesis. A theoretical hypothesis is the one you base your study on, that you craft from your research question based on previous evidence, literature, and conceptual models. A statistical hypothesis is an assumption about a population parameter. It can be used to evaluate whether the actual values of a parameter are equal to the expected theoretical values of that population parameter. You can use your theoretical hypothesis to create a statistical hypothesis, but a statistical hypothesis must be made on parameter estimates and a test statistic. For example, you may think that people with low vitamin D levels are more likely to have severe COVID symptoms. In your research proposal, your theoretical hypothesis might be that patients with below normal serological levels of vitamin D have greater risk of hospitalization from SARS-CoV-2 infection than those with normal levels. But your statistical hypothesis would be constructed for the relative risk of being hospitalized among those who have below normal levels of vitamin D compared to those with normal levels of vitamin D being greater than 1. Your null hypothesis in every case will state that the parameters you are comparing are equal or that there is no difference or no relationship. In public health, we are usually looking for a relationship or difference. So our null hypothesis usually represents that we didn't find the relationships we were looking for in our study. Investigators attempt to reject or retain the null hypothesis, and if they reject the null hypothesis, they can accept the alternative hypothesis. Again, the null hypothesis is represented by H0 and means equality of parameters. The alternative hypothesis is represented by HA or H1 and means inequality of parameters or that some difference exists. Returning to our examples, the null hypotheses are essentially the same in the theoretical and statistical hypotheses, that there is no difference in risk. But in the latter, we also state that the null value is the relative risk equal to 1, or no difference. The intuition behind hypothesis testing is that we're constructing a measure of compatibility between the data we've collected and the null hypothesis. We do this by calculating a test statistic, which is then evaluated in terms of probability. We want to know the probability of getting a test statistic under the null hypothesis that is as extreme or more extreme than the observed value we obtained. We then reject the null hypothesis if the compatibility between the data and the null hypothesis is very low. We use a significance level to indicate how low the probability would need to be for us to find the observed value if the null hypothesis is true. There are 6 steps to hypothesis testing. State the null hypothesis and the alternative hypothesis, specify the level of significance, or alpha, calculate the value of the appropriate test statistic, find the p-value or critical value for this test statistic, and then decide to reject or retain the null hypothesis and state a conclusion that connects the statistics back to the science. The statistical null hypothesis is about a population parameter that a researcher tests. It could be a mean, like mu equals 85, or some certain number, or for our relative measures, it could be that there is no difference, such as relative risk is equal to 1, or odds ratio is equal to 1. The alternative hypothesis is the hypothesis that contradicts the null based on the research question. This could be that simply mu does not equal 85, or that relative risk or odds ratio does not equal 1. The direction of the alternative hypothesis has to be stated before the data are collected and should be visible from the posed research questions. When the alternative hypothesis is non-directional and uses a two-tailed test, we can detect a difference between the true value and the hypothesized value of the parameter, regardless of the direction or the difference. With the directional alternative hypothesis, our focus is only on a difference in the particular direction, and we use a one-tailed test. Those are more powerful than non-directional tests if findings are in the anticipated direction, but they can be limiting or misleading if the findings are not in the anticipated direction. Step 2 is to specify the level of significance, or alpha, which is the probability of rejecting the null hypothesis when it is true, or the risk of rejecting a true null. We typically set this at 0.05, but we may move it to a larger or smaller probabilities. We are examining whether the probability of obtaining the test statistic as extreme or more extreme than the observed result by chance is less than or equal to 5% or 0.05 if the null hypothesis is actually true. Step 3 is to specify the test statistic and sampling distribution. We'll use an example of a z-test, but you may also use t-tests for single means, or for tests of independence, chi-square goodness of fit test, or tests of independence for categorical variables, as well as others. It depends on your hypothesis, but each should have an underlying distribution of which you can compare means or proportions. For each of the test statistics, there's a critical value of the statistic that's calculated using the probability of the distribution. Beyond these critical values in the distribution, the values of the test statistic indicate that the probability of obtaining those values, if the null hypothesis is true, are so small that you would reject the null hypothesis. They serve as the dividing points between the region where the null hypothesis is rejected and where it is retained. You typically need to look these up these values in appropriate tables, like this z-score table, but you'll likely be doing this on software like OpenEpi, EpiInfo, SPSS Data, or R. You can also use an online calculator, but it's helpful to see theoretically what is happening in determining when we reject or retain a null hypothesis. The region of rejection is the region beyond these critical values in the distribution of the score. In this example, a z-score. The region of rejection is the area under alpha, or the significance level. And then the region of retention is 1 minus alpha. This is a two-tailed test, so we find the 0.05 of alpha is split in half to give us two regions of rejection, each of which is at a probability of 0.025. For the z-score, the critical value for alpha equals 0.05 is plus or minus 1.96, as indicated by the purple shaded regions. And for alpha of 0.01, it's plus or minus 2.58. Step 5 is to compare the test statistic and the critical value. If the test statistic, Z or T value, exceeds the critical value, the test statistic falls within the region of rejection, the null hypothesis is rejected. Otherwise, the null hypothesis is retained. In this example, we had, say, a population mean of 85, and the sample mean collected was 90. The z-score calculated was plus 2.50, and you can see that it falls into the upper region of rejection. So we would have evidence to reject the null hypothesis. The further the z-statistic is from 0, the stronger the evidence that the null hypothesis is false. The final step is to make a decision about whether to reject or retain the null hypothesis based on the evidence. We reject the null if the obtained value is more extreme than the critical value, because this tells us that the difference between the values we're comparing is too large to be attributed to chance alone. We can also decide to reject the null based on the probability that the obtained value would appear by chance is less than 5%, 0.05, given a true null hypothesis. We don't reject the null if the obtained value doesn't exceed the critical value, or the probability that the value would appear by chance if the null hypothesis is true is greater than alpha. In summary, we ask, is the mean of the sample different than the mean of the population? Because of the way they are written, the null and alternative hypotheses cover all possibilities. Is the difference between the population mean and the sample mean too large to be due to chance? Extreme means past a critical value, and chances mean the p-value or level of significance. If the mean of our sample is so extreme, meaning it's so far off from the mean of the population that the chances of it being from the same population are very small, we reject the null. If not, then we do not reject the null. Not because we're saying the means are equal, but because we can't say with confidence that they are different. And this applies not only to means, but also to our measures of association, like our relative risk and our odds ratios. If we were to draw more samples of our population, we would get different values for any of our point estimates from each sample, and each of these would give us one estimate of the parameter of interest from the population. Therefore, it seems logical to write down a range of likely values for the parameter of interest. Now, we can expand our simple statistic, our point estimate, to a range of likely values called an interval estimate, demonstrating the uncertainty in the point estimate. The confidence interval takes the form of a lower bound and an upper bound, and what it tells us is the probability that, over repeated sampling, the interval includes the true parameter value. The idea of a confidence interval is that if we took a population parameter we wanted to estimate, like a mean, and we take 100 samples of the population, different samples, and calculate the mean for each one, we would create an interval out of all 100 of the values from the lowest to the highest. We then say that we believe that 95 of these 100 samples values contain the true population mean. Interval estimation provides this range of reasonable values that are intended to contain the parameter of interest, whether that's our mean, risk ratio, odds ratio, with a certain degree of confidence. The parameter of interest when testing a hypothesis is the null value. And since most of our measures of association are relative measures, their null value is 1. So if we calculate a 95% confidence interval of our relative measure, we want to make sure it does not include the null value of 1. If we want to use confidence intervals for hypothesis testing, which we do often when reporting relative measures, particularly crude relative measures, We would say that values between the lower and upper limit of the 95% confidence interval are values for which the null hypothesis would not be rejected because the null value could be within that interval. For example, a population value mean of 85, we would reject the null if the value is not contained in the interval of, for example, 78 to 83. We would reject it if the confidence interval were 78 to 91. For relative measures, we simply want to make sure the confidence interval does not contain 1. Here is a demonstration of where our relative rates, risk and rate ratios and odds ratios, would fall along a continuum of 0 to infinity, given higher or lower values in the numerator or denominator. And we see that the equal values in the numerator and the denominator are 1, no difference. So that gives us the null value of 1. If the confidence interval of your measure overlaps the null value, that indicates that the interval might contain the null value and it is not statistically significantly different than the null value. So we would not be able to reject the null hypothesis. These are examples of relative risks, some that are greater than the null value of 1 and some that are less than the null value of 1 that are statistically significantly different than 1 because they do not cross that null value. And then there are the two at the bottom, that do cross, the interval crosses the null value of 1, so those are not statistically significantly different than the null value of 1, and we cannot reject the null hypothesis. This is the kind of table you would likely see in a study or a report from your study that would contain risk ratios and 95% confidence intervals. Looking at this table with risk ratios for cancer given different levels of exposure, variables of food consumption, genetic mutation, and income, which of these have statistically significant risk ratios as indicated by their confidence intervals? Take a moment to look. Now, what is the null value for a risk ratio? It's 1. So which of these intervals do not contain the null value? In this study, having an unhealthy diet and having an income less than $50,000 a year were significant risks associated with having cancer. And a final note on confidence intervals. Narrow confidence intervals are better. The larger the sample, the narrower become the actual values of the confidence interval and the more precise the prediction. It's desirable to have narrow CIs. Wide confidence intervals have little meaning and usually indicate that your sample size was not big enough for your analysis. In general, if your sample is larger, less variable, or you choose lower confidence, you'll have narrower confidence intervals. We've discussed all these steps of statistical inference, and through these we can make a decision about a population from which a sample was drawn, but we usually don't know for certain the true population. What we can determine is the probability that we have made a correct decision or if we've made an error. In hypothesis testing, there are 2 types of error. Type 1 error is when we reject the null hypothesis when the null hypothesis is true, and type 2 error is when we do not reject the null hypothesis when it is not true. Type 1 error is when you reject a true null. This is also our alpha, or level of significance. It's the probability of getting type 1 error. And you decide this as an investigator. Type 1 error is the level of risk you're willing to take that you will reject a null hypothesis when it is actually true. It's your significance level. When you say p equals 0.05, you're saying that the researcher's decision to reject the null might be incorrect 5% of the time. In type 2 error, this is when we retain a false null. So we failed to reject a false null. And this is called beta. It's the probability of type 2 error. It's not as directly controlled as type 1 error, but instead related to factors such as sample size and our alpha. So as sample size increases, type 2 error decreases. And if other factors are constant, when you raise the significance level from 0.01 to 0.05, then our type 2 error decreases. It is related to power, and that power is 1 minus beta, or 1 minus our type 2 error. Given any parameter we're testing, if we plot the distributions of the values under the null hypothesis and the distribution of the values of the alternative hypothesis, the areas of overlap are the opportunities for error and make up the type 1 and type 2 error. Statistical power, or 1 minus beta, 1 minus type 2 error, is the probability that we reject the null hypothesis when it is false. This is the probability that we make a correct decision when the null hypothesis is false. And the area here under the alternative hypothesis that is not covered by beta is the power. I tried to shade it in orange for you to see that covers the area of alpha as well. There are different factors that affect power, including effect size, or the difference between our H0 and our alternative hypothesis, and power increases with effect size increases. Sample size, as we said, power increases with sample size increasing, and power decreases when variance increases. So it's more difficult to make an association when there's more variance. Power increases when we increase our alpha, and a one-sided test is more powerful than a two-sided test if the direction is correct. And this graph demonstrates how effect size can be affected by sample size. In the first study, with a sample of 1,000, a smaller difference was found between teens belonging to a gang and those not belonging to a gang in mean number of days that they used marijuana. In the second study, which was 1/10 the size of the first, with only 100 teens, a large effect size was found. We want power to maximize the probability that we make a correct decision when the null hypothesis is false, or to reject it. This is what we really want in our samples, in our studies. So what can we be aware of that could decrease power? Power decreases as alpha decreases, because there's a smaller probability of showing the association. As variance increases, as I mentioned, it's harder to show that association with more variance. And as sample size decreases. Small samples can lead to non-significant results that are errors, and large samples can lead to significant results that are errors. So calculate your power for analysis if you can, which is what we'll do in OpenEpi. Now, there's a special way of using error, and that's our screening tests. It's a useful way in which we use error to help us understand tests that screen for disease. So screening tests need to be reliable and valid. Reliability is the ability of the test to give consistent results on repeated trials, so every time it's done, at different times or under differing conditions. It's the test precision. And validity is the ability of the test to give a true measure of the condition. It can distinguish between who has the disease and who does not, and it's the test accuracy. We must have some gold standard test that allows us to know if the disease is truly present or not. But those gold standards are usually really expensive, a biopsy or surgery or autopsy. So we're looking for inexpensive tests that can mimic the gold standard, and then if necessary, we can always follow up with the gold standard. And these are screening tests. A screening test for disease acts basically as a decision to reject or accept the null hypothesis. And in this case, the null hypothesis is that you do not have the disease. So if the null hypothesis is true, then you don't have the disease. If the null hypothesis is false, you do have the disease. The screening test is the decision to reject or retain the null. So if you test positive, you reject the null hypothesis that you have no disease. If you test negative, you retain the null hypothesis that you have no disease. For the best reliability and validity, we want to maximize the true positives and the true negatives. That is, to test positive when you have the disease and to test negative when you do not have the disease. Ideally, all tests would fall into these two categories, but we know tests have error. Here are some examples of type 1 error and type 2 error. In type 1 error, you see a man telling another man, "You're pregnant." So the test is positive, but we know that he cannot be pregnant. So the disease is absent. And in our type 2 error, there's a woman telling a pregnant woman that she is not pregnant. So the condition is present, but the test is negative. In type 1 error, the test is positive and disease is absent. It's measured positive, but the reality is negative. And these are our false positives. In type 2 error, the test is negative, but the disease is present. It's measured negative, but the reality is positive, and that's our false negative. So the sensitivity of a test is the probability of detecting the disease in a diseased person. So it's the proportion of true positives out of everyone who has the disease. The specificity is the probability of clearing a non-diseased person. The test can specify the signal, which is the disease, from noise or the other factors. And for this, we measure the proportion of true negatives out of all of those without the disease. Sensitivity is the ability of the test to correctly identify all screened individuals who actually have the disease. If it's highly sensitive, it minimizes those false negatives. So a sensitive test with a negative result can rule out the disease. And specificity is the ability to correctly identify only non-diseased individuals who do not have the disease. If the test is highly specific, it minimizes false positives. So a specific test with positive results rules in disease. Here is another one of our graphs where, just like our graph of error, the true negatives are the distribution on the left in green, and the true positives are the distribution on the right in red. A indicates a test with 100% sensitivity, and B indicates a test with 100% specificity. And you can see where these tests create type 1 and type 2 error in the areas under the curve, creating false negatives and false positives. The relationship of sensitivity and specificity is such that increasing one is going to contribute to the other. So to increase sensitivity, you might shift the red line in the middle where the test line is to the left to where the purple line is, and you will catch more people who have the disease, but you're also going to increase the proportion of false positives, which means you're reducing the specificity. Likewise, if you want to increase your specificity and you shift to the right, you're going to capture more patients without the disease. But by shifting to the right, you're going to increase your proportion of false negatives, which means reduced sensitivity. And this is a little guide to how to interpret sensitivity and specificity. And finally, I want to introduce you to a software program called OpenEpi that you can use to calculate sample size, statistical power, as well as do randomization, and all kinds of other really helpful calculations for conducting research studies. I am going to do that in a separate video, so that this one isn't too long. Today we've covered a lot on the process of statistical inference, or using the data you collect from a population on your sample to make inferences about that population. We've covered how to sample a population, to make observations of variables and estimate our population parameters, to quantify our degree of certainty or uncertainty in the sample estimates reflecting the population parameters, and to make inferences about the population from these data. My final thoughts are that there are many steps in the process of statistical inference, but they are all so very important to build confidence in your study results and in generalizing your study results back to the population that you believe your sample represents. So I thank you.